Have you ever looked at a really sleek car or even a golf ball with all those dimples and thought, why exactly does it look like that?
Yeah, it's definitely not just about looks, is it?
Not at all. Today we're going to take a deep dive into something called external forced convection. Basically, how fluids think air or water move over solid objects.
And the forces involved,
hmm
the energy transfer.
Yeah,
It's everywhere once you start noticing.
absolutely. It's fundamental to designing planes, cars, even cooling the electronics you're probably using right now.
hmm
So our mission today, we want to give you a shortcut, really, to getting your head around this. We'll unpack the core ideas, things like drag and heat transfer.
And we'll distinguish between flow over something versus flow through something, like in a pipe. That's key.
Right, and then we'll get specific. We'll talk flat plates, then cylinders,
And those
spheres.
big tube banks you see in industrial settings.
Exactly. And all this insight, it comes straight from a pretty detailed textbook chapter on this exact subject. So expect some surprising facts, some really practical examples.
Yeah, stuff that explains a lot about how the engineered world actually works.
Okay, so let's unpack this.
Let's do it.
First off, external flow. What are we actually talking about?
Okay, so external flow means a fluid flowing over the surface of some solid object.
Like wind hitting a building, or water flowing around, say, a boat.
Exactly. It's not like water flowing inside a pipe. That's internal flow.
And that difference, it seems small, but it's actually a really big deal for design, right?
Huge deal. Yeah. It affects how you design, well, almost everything. Airplanes, electronics, cooling, turbine blades, and power plants. The list goes on.
Okay. And when you have this fluid flowing over a body, there's always a force pushing back, resisting the motion.
That's drag.
Drag, simple term, but pretty important. It's the force the fluid exerts on the object, right in the direction the fluid's moving.
And you've definitely felt it. Stick your hand out of a moving car window.
Oh, yeah. That push.
That's drag. Plain and simple.
But it's not quite that simple, is it? Because that resistance, that drag force, it actually comes from two different places.
Exactly. It breaks down. First, you have what's called friction drag. Skin friction, some call it.
Skin friction. Okay, so that sounds like rubbing.
Pretty much. It's
Yeah.
caused by the fluid's viscosity, its stickiness, creating shear forces right on the surface. It's
Yeah.
like the fluid is literally rubbing against the object.
And that's more important for certain shapes.
Yeah, it tends to dominate for slender bodies.
Mm-hmm.
Think like a thin, flat plate lined up perfectly with the flow. More surface area generally means more friction drag.
And surface roughness matters too, you said, especially if the flow is turbulent.
Oh, absolutely. A rougher surface in turbulent flow can really crank up the friction drag.
Okay, so that's friction drag. What's the other type?
The other one is pressure drag, sometimes called form drag. This one's all about pressure differences.
How so?
Well, you get high pressure on the front of the object where the fluid kind of slams into it. But in the area behind the object, the wake, you get a region of much lower pressure.
Ah, okay, so the difference between the high pressure pushing on the front and the low pressure sort of pulling from the back.
Exactly. That pressure difference creates a net force pushing the object downstream. That's pressure drag.
And this one is bigger for less streamlined shapes, blunt bodies.
Yes, exactly. Like a flat plate turned sideways to the flow. Pressure drag is dominant there, and it's generally proportional to the frontal area, the area facing the flow directly.
It's fascinating how it splits like that.
It is. And engineers, they spend a lot of time trying to play these off against each other. Streamline a car to cut pressure drag.
But maybe that increases the surface area, bumping up friction drag?
Precisely. It's often a trade-off, especially at different speeds. Finding the sweet spot to minimize the total drag is the goal.
You mentioned the wake, that low pressure zone behind the object. That seems pretty important for pressure drag.
It's crucial. When the fluid flow pulls away from the surface, we call that flow separation, it creates this messy, turbulent region behind the body,
The wake.
the wake. And that low pressure in the wake is the main driver of pressure drag for blunt bodies. Think about the swirling air behind a moving truck or a tennis ball.
Okay, I can picture that. And how do engineers measure this? Like, compare drag for different shapes?
They use a dimensionless number called the drag coefficient, usually written as CD.
Ah, dimensionless numbers. Always useful in engineering.
They are. CD basically bundles up the effects of shape, fluid density, velocity, and some characteristic area, frontal area, for pressure drag, maybe surface area for friction drag. It gives a standard way to compare how draggy different shapes are.
Makes sense. And quickly, these same forces, the pressure and the shear forces, they also create lift, right? The force perpendicular to the flow.
That's right. Same origins, different direction, obviously critical for things like airplane wings.
Okay, so we've got drag. Now, how does heat transfer tie into all this?
Well, they're very closely linked. The same things that affect drag the boundary layer, turbulence, flow separation, they also heavily influence how heat moves between the object and the fluid.
So the fluid dynamics drives the thermal behavior.
Exactly. For heat transfer, the key dimensionless number is the Nusselt number.
Nusselt number. Okay,
Yeah.
what does that tell us?
It essentially compares the actual convective heat transfer to what you'd get just by pure conduction through the fluid if it weren't moving. A higher Nusselt number means more effective heat transfer because of the fluid motion.
And what determines the Nusselt number?
It mainly depends on the Reynolds number.
Which we mentioned relates to flow speed and viscosity, kind of inertia versus stickiness.
Precisely. And also the Prandtl number.
Prandtl number, what's that one about?
The Prandtl number is pretty neat. It's a ratio that tells you how fast momentum diffuses in the fluid compared to how fast heat diffuses.
So how quickly the fluid's motion spreads versus how quickly temperature changes spread?
You got it. Some fluids, like oils, have high Prandtl numbers. Heat spreads slowly compared to momentum. Liquid metals have very low Prandtl numbers, heat zips through really fast. Air and water are somewhere in the middle.
Interesting. Okay, so for doing actual calculations, how do engineers handle fluid properties like viscosity or thermal conductivity, which change with temperature?
Good question. Often they use something called the film temperature.
Film temperature.
Yeah, it's just a simple average temperature between the object's surface and the main fluid stream, far away from the object.
So surface plus T free stream divided by 2.
Exactly. Evaluating the fluid properties at that average temperature usually gives a pretty good approximation for what's happening in the boundary layer where all the action is.
Okay, simplifies things. And are engineers usually looking at heat transfer at one specific spot or overall?
Usually, the main interest is the average heat transfer coefficient over the entire surface. You can calculate local coefficients at different points, and sometimes that's important, but often you integrate those local values to get the average for the whole object.
Got it. Okay, let's make this more concrete. Let's talk about the classic starting point. Flow over a flat plate. Parallel flow.
The fundamental case, yeah. Imagine air flowing smoothly over a long, flat board lined up with the flow.
What happens?
Well, right at the leading edge, the flow is smooth and orderly. That's laminar flow. The fluid moves in nice parallel layers.
Okay, but it doesn't always stay that way.
Nope. If the plate is long enough, or the flow fast enough, the flow eventually becomes chaotic and highly mixed. That's turbulent flow.
And there's a tipping point.
Yeah, there's a critical Reynolds number where this transition typically starts. For flow over a flat plate, it's usually taken to be around 500,000. So Recker equals 5 times 10 to the 5th.
500,000. Okay. And how does this affect friction and heat transfer?
Well, interestingly, both the local friction drag coefficient and the local heat transfer coefficient are theoretically infinite right at the very start, the leading edge.
Infinite?
Theoretically, yeah, because the boundary layer thickness is 0 right there. But then they both decrease as you move downstream along the plate.
And when it becomes turbulent?
In the turbulent region, both friction and heat transfer coefficients jump up significantly. They become much higher than in the laminar region because all that chaotic mixing brings faster moving, often hotter or colder, fluid right down to the surface.
More mixing means more transfer, basically.
Exactly. But even in the turbulent region, the coefficients still generally decrease as you continue further down the plate, just from a higher starting point.
Okay, this laminar turbulent transition seems really important. Does it have practical consequences?
Absolutely. Let's look at a real-world safety example. Imagine you have a hot engine, maybe with an insulated cover.
Okay.
And let's say the inner surface of that cover gets really hot from the engine exhaust, maybe 350 degrees Celsius.
Pretty hot.
Very hot. Now, the danger is if some oil, maybe leaking oil, drips onto the outer surface of that cover. If that outer surface gets too hot, the oil could spontaneously ignite. Big fire hazard.
Right. So you need to keep that outer surface cool enough, let's say below 180 degrees, the auto ignition point for the oil.
Precisely. So the engineers look at cooling that outer surface with air flowing over it. Let's say the cover is 2 meters long, and the air is initially flowing at 7 meters per second.
Okay.
They do the calculations and maybe find the outer surface temperature still a bit too high, maybe slightly above 180 degrees Celsius, not safe.
So what do they do? Increase the airflow.
Exactly. But here's the cool part. They increase the air velocity by just 10%, from 7 meters up to 7.7 meters.
Yeah.
Seems like a small change, right?
Yeah, it doesn't sound like much.
But that small increase was enough to push the Reynolds number just over that critical value of 500,000. It went up to about 610,000.
Ah, so it triggered the transition to turbulence over part of the plate.
Bingo. So now you have combined laminar and turbulent flow over the surface. And because turbulent flow transfers heat much more effectively,
The surface temperature dropped.
drops significantly. The calculation showed it went down to 173.5 degrees Celsius, safely below the ignition point.
Wow. So that tiny 10% increase in speed, just by triggering turbulence, solved a major safety problem.
It's a perfect example. It shows how crucial understanding that transition point and the difference between laminar and turbulent heat transfer can be. Sometimes a small tweak makes all the difference.
That's a great illustration. Are there other wrinkles with flat plates?
Yeah, a couple of things sometimes come up. One is called the unheated starting length.
Meaning part of the plate isn't heated?
Right. If the flow develops over a section of the plate before it hits the heated part, that affects how the thermal boundary layer grows and changes the heat transfer calculations for the heated section.
Okay, you have to account for that initial unheated run.
You do. Another situation is uniform heat flux. Sometimes, instead of keeping the plate at a constant temperature, you have a constant amount of heat flowing into the plate per unit area.
Like an electric heater element inside?
Could be, yeah. In that case, the surface temperature isn't constant. It actually varies along the plate, and you need different equations to figure out that temperature profile.
Okay, so different boundary conditions require different approaches. Makes sense. But flow isn't always over nice flat plates. What about curves? Cylinders, spheres?
Right, the blunt body challenge. And these shapes are everywhere, aren't they? Tubes and heat exchangers, pipes, sports balls.
Golf balls. We mentioned golf balls.
We did. And flow around these blunt shapes is, well, way more complicated than over a flat plate aligned with the flow.
Why is it so much trickier?
The main reason is that flow separation happens much earlier. The fluid just can't hug the surface around the sharp curves on the backside.
So it pulls away.
It pulls away, creating those large, messy, turbulent wakes we talked about earlier.
And those wakes mean low pressure behind the object.
Which means significant pressure drag. Remember, high pressure on the front at the stagnation point. That's the point right at the very front where the fluid stops for an instant, and low pressure in the wake. That difference is the big driver of drag for blunt bodies.
Okay, that makes sense. High pressure drag because of the wake. So faster flow, bigger object. Just means more drag, right? Seems intuitive.
Ah, you'd think so.
Yeah.
But here's where things get really interesting, kind of weird even. It's called the drag crisis.
Drag crisis sounds dramatic.
It is in fluid dynamics terms. For cylinders and spheres, under the right conditions, the drag coefficient can suddenly drop dramatically, plummet even.
The drag decreases as speed increases. How does that work?
It usually happens around a specific Reynolds number, typically around 2 times 10 to the 5th for a smooth sphere or cylinder. And the why is fascinating. It's that laminar to turbulent transition again, but this time happening in the boundary layer on the object itself.
Okay, so the flow right next to the surface becomes turbulent.
Exactly.
Yeah.
And turbulent boundary layers have more energy, more momentum near the surface compared to laminar ones.
So they can fight against the pressure changes better.
Precisely. That extra momentum allows the turbulent boundary layer to stay attached to the surface longer as it flows around the back of the sphere or cylinder. It pushes the separation point further downstream.
So the wake behind the object becomes narrower?
Much narrower. And a narrower wake means less low-pressure area pulling backwards.
Which means less pressure drag.
Yeah.
Significantly less.
Bingo. The overall drag drops sharply. It's turbulence actually reducing drag, which is totally counterintuitive at first glance.
And the classic example, everyone knows it, is the golf ball.
The perfect example. Those dimples aren't just decoration. They deliberately roughen the surface.
To make the boundary layer turbulent sooner?
Yes. That roughness trips the boundary layer into becoming turbulent at a much lower Reynolds number, maybe around 4 times 10 to the 4th, well before it would happen on a smooth sphere.
So the golf ball enters its drag crisis mode at the speeds it actually travels.
Exactly. And this reduces its drag by roughly half compared to a smooth ball of the same size traveling at the same speed.
Which lets it fly much, much farther. Amazing.
It really is. Contrast that with, say, a smooth ping pong ball. It just never reaches high enough Reynolds numbers in normal play for this effect to kick in, so dimples wouldn't help it.
That makes so much sense now. And these drag forces, they can be really significant, right? Even in seemingly normal
Oh,
situations.
absolutely massive sometimes. Consider this. A simple pipe, maybe 2.2 centimeters in diameter, less than an inch, stretched across a 30-meter wide river where the water's flowing at, say, 4 meters per second. Not exactly raging torrent.
Okay, seems reasonable.
The drag force in that relatively small pipe from that moderate flow is equivalent to hanging over 500 kilograms of mass from it.
Wow, half a ton just from water flowing past a small pipe.
Yeah. It really puts into perspective the kind of forces engineers have to design for when building bridges, offshore platforms, anything interacting with moving fluids. They're often underestimated.
Definitely makes you appreciate the power of flowing fluids. Now, what about heat transfer for cylinders and spheres? Is it uniform?
Not at all. It varies quite a bit around the surface. The local heat transfer coefficient is actually highest right at the front, at the stagnation point.
Where the fluid hits directly?
Yep. Then, as the boundary layer grows thicker, moving around the sides, the heat transfer decreases.
But what about the wake? It's turbulent back there.
Good point. In the separated wake region, the intense mixing actually causes the heat transfer coefficient to increase again. So it's high at the front, dips around the sides, and rises again on the back.
Quite complex, so how do engineers calculate the average heat transfer?
Because the flow is so complex, they generally rely on well-established experimental correlations equations based on lots of test data. People like Churchill and Bernstein developed widely used ones for cylinders, and Whittaker for spheres, relating the average Nusselt number to the Reynolds and Prandtl numbers.
Empirical correlations based on data. Got it. Okay, let's scale up now. From single cylinders to banks of them. 2 banks.
Right. These are the heart of many large-scale heat exchangers. Think condensers and evaporators and power plants, big industrial refrigeration units, stacks and stacks of tubes with one fluid flowing over them and another fluid flowing inside them.
And I guess the flow over a whole bank of tubes is different from flow over just one isolated tube.
Oh, completely different. You can't just take the result for one tube and multiply. Each tube messes up the flow for the tubes behind it.
Creates more turbulence.
Exactly. The flow becomes much more complex and turbulent as it navigates through the bundle. The tubes interact strongly with each other, hydrodynamically.
And how the tubes are arranged must matter too.
Definitely. They're usually arranged in repeating patterns, either in line, where tubes in consecutive rows are directly behind each other.
Like a grid.
Yeah. Or staggered, where tubes in one row are shifted to sit in the gaps between tubes in the previous row.
Like bricks in a wall.
Good analogy. And the spacing matters too, the distance between tubes side to side, transverse pitch, and front to back, longitudinal pitch. These define the geometry.
Okay. And when calculating things like Reynolds number for a tube bank, what velocity do you use? The speed the fluid comes in at?
Not usually. Because the fluid has to squeeze through the narrow gaps between the tubes, its velocity actually increases inside the bank.
Ah, the flow speeds up in the constricted areas.
Right. So the Reynolds number for tube banks is typically based on the maximum velocity the fluid reaches as it passes through the tightest spot between tubes in a row.
Okay, Vmax. Got it. How does heat transfer behave as the fluid moves through the bank?
Well, similar to the wake effect on a single cylinder, the turbulence generally increases as the flow penetrates deeper into the bank, at least for the first few rows.
So heat transfer gets better for the first few rows.
Yes, the heat transfer coefficient tends to increase row by row initially, but after maybe the third or fourth row, the turbulence level kind of stabilizes, and the heat transfer coefficient becomes relatively constant for all the deeper rows.
Interesting. So there's an entrance effect, then it settles down.
Pretty much. And again, engineers rely on specific correlations, like those developed by Zhukauskas, to find the average Nusselt number for the whole bank. These often include correction factors if the bank has fewer than, say, 16 rows, to account for that entrance effect.
Makes sense. Now, heat transfer is usually the goal, but there's always a cost, right? The fluid doesn't flow through for free.
Absolutely not. There's always a pressure drop. As the fluid fights its way through that complex maze of tubes, it loses pressure due to friction and all the twists and turns.
And that pressure drop is basically a measure of the resistance the tube bank offers to the flow.
Exactly. It's an irreversible pressure loss. And why is that so important?
Pumping power.
Pumping power. The energy you need to expend to push that fluid through the bank is directly proportional to the pressure drop.
So high pressure drop means high energy consumption, high operating costs.
Precisely. Especially in large industrial systems. Minimizing pressure drop while still achieving the necessary heat transfer is a huge economic driver. It's all about energy efficiency.
It connects back to the big picture: energy use, costs, environmental impact.
It really does. Optimizing these tube bank designs is fundamental to energy efficiency across countless industries, from massive power generation down to the air conditioner cooling your home. It's a core engineering challenge. Get the heat transfer you need without paying too much in pumping power.
Let's ground that with one last example. Say, preheating air for an industrial furnace.
Okay.
You could use geothermal water flowing inside the tubes of a tube bank to heat up air flowing over the tubes before it goes into the
A
furnace.
common application saves fuel for the furnace.
Right. So the engineers designing the system, they need to calculate two main things based on what we've discussed.
Yep. First, how much heat is actually transferred from the hot water to the air? Does it meet the preheating requirement?
And second,
Second, what's the pressure drop of the air as it flows across that tube bank? Because that determines how big the fan needs to be and how much electricity that fan will consume.
so you need both: heat transfer effectiveness and the cost of achieving it via pressure drop.
Exactly. It shows perfectly how these calculations are completely intertwined with both the energy performance and the economic viability of the system.
Fantastic. So just to wrap up here, we've covered quite a bit of ground,
We have, from the basics of external flow
distinguishing friction and pressure drag,
to the surprising drag crisis on spheres and cylinders,
the nuances of flow over flat plates, including that laminar turbulent transition.
and finally the complexities of heat transfer and pressure drop in industrial tube banks.
You hopefully have a much better feel now for how engineers approach these problems, designing everything from faster golf balls to more efficient power plants.
These aren't just abstract textbook concepts. They are literally the invisible forces shaping the performance and efficiency of so much around us.
From how fast your coffee cools down to how much energy it takes to run our industries, it's all governed by this interplay of fluid flow and heat transfer.
So maybe think about this. What stood out most to you listening today? Could understanding something like the drag crisis, or how surface roughness changes things, spark an idea in a totally different field?
Yeah, like could these principles apply to optimizing blood flow in arteries? Or maybe designing cities to manage wind and temperature better?
The fundamental physics are the same, applying them in new ways. Well, that raises some important questions, and the possibilities are pretty much endless.